We have been trained to think harvesting the sun means spending thousands of dollars on high-tech silicon panels and complex inverters. Fragile black box systems you cannot build. Systems you cannot repair when they degrade. Systems that eventually fail and leave you dependent on replacement parts, installers, and electronics you do not control. But there is another way to harvest solar energy, and it has been known for hundreds of years. It does not start with silicon. It starts with the basic laws of thermodynamics and common materials you can find at a local hardware store. Glass, water, mirrors, that is the overlooked part. While the solar panels on your neighbor's roof struggle to reach 20% efficiency, this discarded method can achieve a conversion rate of nearly 70%. That means it can outperform even advanced industrial engines while using materials that look almost too simple to matter. So what is this forgotten technology? How does it actually work? And why are we not installing this instead of photovoltaics? To find the answer, we have to go back to a time before the world became addicted to the centralized electrical grid. In 1866, a mathematics professor named Augustin Mouchot stood in the courtyards of France and demonstrated a machine that turned sunlight into mechanical power. The machine used a massive conical mirror. That mirror focused sunlight onto a glass-covered boiler. The idea was direct and practical. Capture the sun as heat. Concentrate that heat. Use it to make steam. At the time, France was afraid of its dependence on British coal. So Mouchot was tasked by the emperor to find an alternative. And his device did not just look interesting. It worked. It produced enough high-pressure steam to drive a mechanical engine. That proved something important long before the first silicon solar cell was ever imagined. The sun's heat was not just warmth. It was an industrial force. It could be gathered. It could be focused. It could be made to do work. Mouchot's machine became so effective that in 1878 it was displayed at the World Expo in Paris. There, he connected it to a heat-powered refrigeration device and produced ice blocks in front of amazed crowds. A mirror using sunlight to make ice. That is the kind of solar logic we almost lost. The next step in this story moved solar thermal power out of France and onto the banks of the Nile. In 1913, an American engineer named Frank Schumann built the Mahdi power plant. It was the world's first large-scale solar irrigation system, and it proved that this was not just a clever demonstration for a crowd. It was working infrastructure. Schumann understood something that modern solar marketing often buries. The most efficient way to capture the sun is not always through complex chemistry. Sometimes it is through simple geometry. He built 5 massive parabolic troughs. Each trough was nearly 200 feet long. These mirrors tracked the sun and focused its energy onto a central cast iron pipe. That pipe boiled water. The boiling water produced steam. And that steam drove a 60-horsepower engine that pumped 6,000 gallons of water per minute. This was not a toy. This was solar power doing industrial work in the real world. Schumann was not a dreamer pretending coal did not matter. He was a pragmatist. He looked at the world's coal reserves and understood they were finite. Then he predicted that within a century, the Sahara Desert could become the engine room of the planet. His point was simple. For the price of common glass and iron, a nation could own its power source outright. But that vision was stopped almost overnight. World War I broke out. Then cheap, seemingly infinite oil was discovered in the Middle East. And the world turned away from solar thermal logic. Not because it failed, because oil fit the new energy business better. The emerging energy monopolies of the 20th century realized something important. Oil could be metered. It could be shipped. It could be sold again and again. A mirror that harvests sunlight does not create the same kind of monthly dependency. That is the background you need before comparing this system with a modern silicon panel. Because the reason it can outperform photovoltaics is not magic. It is the difference between chemistry and concentration. A standard solar panel relies on the photovoltaic effect. That is a chemical reaction that happens when photons strike a semiconductor. The problem is that this process is naturally limited by quantum physics. Even the most expensive panels on the market are forced to throw away 80% of the energy they receive. The forgotten thermal method takes a different path. It ignores electricity at first. It goes straight for the raw heat of the sun. And the difference between those two approaches is massive. It is like trying to catch water from a tap with a sponge instead of a bucket. The key to this system is the parabolic curve. That curve is what turns a mirror into a heat engine. When sunlight hits a flat surface, the rays reflect in one broad direction. The light spreads out, and the heat stays weak. But when you bend a reflective surface into a precise mathematical curve, every photon that hits it is redirected toward one concentrated line. That line is the focal point, and the focal point is where the system becomes powerful. You are not just catching sunlight, you are multiplying its intensity hundreds of times over. Then you place a pipe at that exact focal line. The pipe is filled with a carrier fluid, usually water or oil. Now the mirror is feeding concentrated heat into a thermal trap. Because the pipe is encased in a glass vacuum tube, the heat can get in, but it cannot escape easily. That concentration can create temperatures that easily exceed 572 Fahrenheit. At that level of heat, the water inside the pipe undergoes a phase change. It turns into high-pressure steam. That is the moment a simple pipe becomes a power plant. In a modern setup, the heat does not have to be used immediately. It can be sent into a heat battery. That battery can be a simple insulated tank of salt or sand. During the day, the sun charges the thermal battery. At night, you draw from that stored heat. When power is needed, the stored heat boils water again. The steam drives a mechanical piston or a turbine. This is the storage advantage almost nobody explains. You are not trying to store electricity inside a fragile chemical battery. You are storing heat directly. And heat is much easier and cheaper to store than electricity. A black box solar panel becomes a useless sheet of glass the moment an internal circuit fails. You cannot see the problem. You cannot repair the chemistry. But this thermal logic is transparent and mechanical. If the pipe leaks, you solder it. If the engine stalls, you turn a wrench. The system is understandable because it is built around heat, pressure, and motion instead of hidden semiconductor electronics. You are harvesting the friction of atoms rather than the flow of electrons. That is why this method can reach an efficiency rate silicon simply cannot match. For the homesteader, that changes what solar power means. It is not just a gadget on a roof. It is permanent industrial infrastructure. A system that can be repaired, upgraded, and kept alive because it runs on focused sunlight and stored heat. The logic of Frank Schumann and Augustin Mouchot never actually disappeared. It was simply moved out of sight. And that matters, because we have been taught to think of solar power as a grid-dependent electronic consumer product. A panel, an inverter, a contract with the utility. A system that only feels complete when it is plugged into the larger electrical machine. But the world's most efficient energy projects have quietly returned to the older thermal foundation. Why? Because thermal solar solves the problem that still haunts the renewable energy industry. Storage. That is the part electronics keep struggling with. But heat can be captured directly, stored directly, and used directly. And this technology is no longer limited to the high deserts of Spain or massive utility-scale plants. For the modern homeowner, the real revolution is miniaturization. The solar trough is shrinking. That shift is called micro-CSP. And the point of micro-CSP is simple. Capture heat first. Do not waste energy forcing sunlight through an indirect electrical conversion if the job you need is thermal. The evidence is in the efficiency math. Standard photovoltaic panels struggle to convert even 20% of the sun's rays into usable power. But research published in journals like Energy and Renewable Energy confirms that small-scale parabolic troughs can capture nearly 70% of that same incoming energy. That is not a small improvement. That is a different class of machine. The jump comes from focusing sunlight onto a single high-performance receiver tube. And recent experimental analysis on surface treatments shows why that receiver matters. Black oxide coatings can increase the temperature delta of the heat transfer fluid by over 60%. So this is not just about making lukewarm water for a shower. It is about producing high-grade thermal energy exceeding 392 Fahrenheit. At that point, a backyard collector stops being a novelty. It becomes a private, high-pressure power plant. The real beauty of this thermal approach is not just the collector. It is the storage, and that is where the modern all-electric home starts to look strange. It is mathematically absurd to use electricity to create heat, then struggle to store that electricity in expensive batteries, when heat was the thing you needed in the first place. But that is exactly what the modern grid-tied home often does. It takes sunlight, turns it into electricity, runs it through electronics, then uses that electricity to make heat again. A domestic trough skips that wasteful loop. By bypassing the electrical conversion, it can feed boiling water or steam directly into the home's thermal infrastructure. That means heat for water, heat for floors, heat for mechanical work, and heat that can be stored without needing a lithium-ion battery bank. Studies featured in the Journal of Energy Storage highlight that holding this energy in heat batteries, using pressurized water, sand, or phase change materials, is significantly more cost-effective than storing it in lithium-ion banks. That is the storage advantage. These thermal systems can operate with a round-trip efficiency of 95%. And unlike chemical batteries, they show no signs of degradation even after thousands of cycles. No slow capacity fade, no expensive replacement schedule, no fragile chemistry wearing itself out every time you charge and discharge it. You are storing heat in mass, and heat stored in mass is simple, durable, and extremely hard to beat. This thermal logic offers a level of energy density that electricity simply cannot match. That is why the financial payback changes so dramatically. A DIY parabolic trough uses accessible materials like polished aluminum and steel tubing instead of specialized semiconductors. So the initial investment is only a fraction of a commercial install. When it replaces high-cost resistive electric heating, the levelized cost of heat from a domestic trough can drop to approximately 3 cents per kilowatt-hour. That creates a payback window of just 2 to 5 years. Compared with the decade-long wait often associated with residential photovoltaics, that is a completely different investment timeline. And the usefulness does not stop at heating water. Recent data on double-effect absorption cooling has shown that a modest residential array can meet nearly 40% of a building's cooling needs, and 20% of its heating demands at the same time. That is the power of owning heat directly. When you own the heat, you own the fundamental currency of survival. You can cook, you can wash, you can warm your home, you can drive machinery, and you can do it without needing permission from a utility provider or depending on a fragile global supply chain of rare earth minerals. By reclaiming the 70% efficiency of concentrated thermal systems, the DIY practitioner stops being only a consumer of a metered product. They become a harvester of a permanent, inflation-proof resource. So if the physics are stronger, the storage is cheaper, and the history already proved the concept, the obvious question is simple. Why are we not all putting parabolic troughs in our own backyards? The answer is not hidden in the mirror. It is hidden in the incentive structure of the 20th century. Just as Frank Schumann was proving that the solar-to-steam cycle could work at industrial scale, the geopolitical landscape changed. Massive, easy oil reserves were discovered in the Middle East. That oil was dense energy. But even more important, it was a product that could be metered, shipped, taxed, and sold through a centralized system. Parabolic solar technology works in the opposite direction. It is the ultimate homestead technology. Because it concentrates light to temperatures flat plate collectors cannot reach, it gives a homeowner access to the kind of high-grade thermal energy usually reserved for factories. Once you install a tracking trough and an insulated storage tank, your marginal cost for high-pressure steam and heat is zero. You are not buying a recurring product anymore. You are harvesting a permanent resource. And for a utility company built around monthly billing cycles, that is an existential nightmare. A permanent heat source does not behave like a monthly bill. Photovoltaics gained traction not because they were the most efficient way to power a home. They gained traction because they fit the industrial model. PV panels are complex to manufacture. They require billion-dollar fabrication plants. They depend on a global supply chain of rare earth minerals. And because they produce low-voltage electricity instead of raw, high-grade heat, they need specialized inverters and restrictive grid tie contracts. That keeps the utility company in the middle. Even when the sunlight lands on your roof, the system still makes the utility part of the transaction. Flat plate collectors were pushed into the narrow role of simple domestic hot water. But the parabolic trough was kept mostly out of the domestic market for a different reason. It offered too much independence. Its efficiency, often cited in renewable energy journals as triple that of PV for thermal applications, made it harder to fold into the normal utility business model. That is why the trade we made looks so strange in hindsight. For decades, we traded the 70% direct efficiency of concentrated thermal systems for the 20% efficiency of electronics. Not because electronics were better at capturing heat, because they were easier to monetize, and easier to control through billing, contracts, and replacement cycles. For the modern home, the parabolic trough is not another solar device. It is an argument for radical decentralization. When you move away from the all-electric home, you also move away from the fragility of the grid. That is the part most energy conversations skip. We did not choose PV because it was the best way to cook a meal. We did not choose it because it was the best way to run an air conditioner. And we did not choose it because it was the best way to heat a floor. We chose PV because it was the best way to build an industry. A domestic solar trough works on a different logic. To install one today is to reclaim lost process heat. It means opting out of a system that would rather sell you an expensive chemical battery than let you store the sun's focus in pressurized water. For energy independence, the transition from consumer to producer begins with one calculation: the concentration ratio. To build a functional solar thermal collector, you do not need a laboratory. But you do need to understand the relationship between the surface area of your mirror and the surface area of your receiver pipe. That relationship determines how much sunlight becomes concentrated heat. A successful domestic trough typically aims for a ratio of at least 15:1. That means for every 6 inches of mirror width, the sun's energy is compressed onto a half-inch wide pipe. That compression is the difference. It is what separates a parabolic trough from a standard flat plate heater. One gives you lukewarm water. The other gives you high-grade thermal energy that can truly run a home. The most accessible path to that level of power is the linear parabolic trough. The design is direct. A sheet of polished aluminum, or a silvered mylar film, is backed by a rigid parabolic rib frame. That curved surface focuses sunlight onto the receiver line. With that setup, the collector can reach temperatures over 392 Fahrenheit for a fraction of the cost of a single PV panel. Once you understand that number, the solar conversation changes. You are not just offsetting watts on a utility bill. You are concentrating sunlight into useful heat. Heat that can cook, heat water, warm floors, and do the energy work electricity usually gets forced to handle. For most people, the first real obstacle in this build is not the mirror. It is the tracking system. Because the sun keeps moving, a stationary mirror will lose its focus within minutes. That is the weakness of concentrated solar. The mirror only works when reflected sunlight stays locked onto the receiver pipe. If the focus drifts, the heat drops. When a trough is aligned on a north-south axis, industrial plants usually solve that problem with computerized GPS trackers. Those systems keep the mirror following the sun's arc throughout the day. But a homesteader does not need the full industrial version. A simpler active tracker can use a pair of photoresistors and a low-speed motor to keep the trough aimed at the sun. The goal is not complexity. The goal is focus. Keep the light on the pipe, and the system keeps producing high-grade heat. There is another option too. The trough can be aligned on an east-west axis. That reduces the collector's overall efficiency, but it also simplifies the build because the trough only has to be adjusted with the seasons. That avoids the need for tracking motors. But here is the deeper point. The real secret to off-grid success is not the collector. It is the thermal store. To achieve true energy independence, you stop chasing expensive, short-lived electrical batteries. Instead, you pipe the high-grade heat into a heat battery. That heat battery can be a heavily insulated tank of pressurized water. Or it can be an experimental sand-based system. Either way, the goal is the same: high-density storage. Research from the University of Kassel and the Solar Fire Initiative confirms that a wool-insulated thermal store can retain over 90% of its energy for more than 24 hours. That changes the timing problem. You can harvest the peak intensity of a Tuesday afternoon. Then use that stored heat for high-pressure steam, cooking, or radiant floor heating on a rainy Wednesday morning. If you want a community-validated starting point, the open-source movement gives you the blueprints for agency. George Plock has a great website with practical information and advice on parabolic trough construction and application. Definitely worth a look. The parabolic solar trough bridges two worlds. On one side is the mechanical genius of the 19th century: mirrors, steam, pipes, and heat you can see, store, repair, and use. On the other side are the energy needs of the 21st century: security, independence, and resilience in a world built around metered grids. That is why this technology matters. A focused reflection can provide more energy security than a decade of battery innovation. By choosing concentration over chemistry, you stop treating solar as a sealed electronic product. You start treating it as a physical law. Sunlight becomes heat, heat becomes work, and work becomes independence. When you own the heat, you own the ability to cook, to cool, and to power your life on your own terms. A lot of what this channel covers was nearly lost, not because it stopped working, but because the industry moved on to something more profitable to sell you. They traded 70% thermal efficiency for a technology that was easier to build, package, and meter. But the old physics never stopped working. It was pushed behind a more profitable business model. If discovering the lost art of high performance, decentralized energy matters to you, subscribing and sharing is the simplest way to make sure this knowledge keeps being found. And if you want to see how these same principles of fluid dynamics can provide a house with a continuous baseload of power for 50 years, using nothing but a backyard stream, you need to see our breakdown on the Pico hydro generator right here.